Welcome to Section 7, Lesson 3. In the previous lesson, we added and subtracted polynomials using the like terms rule. Today, we tackle polynomial multiplication, which uses the distributive law applied repeatedly. The mechanic is mechanical and produces exact answers reliably for any pair of polynomials, regardless of how long either polynomial is. Multiply every term of the first polynomial by every term of the second polynomial, then collect like terms. The degree of the product equals the sum of the input degrees, and the leading coefficient of the product equals the product of the input leading coefficients. Today, we lock in the distribute, everything mechanic, the like term collection step, and the structural relationships between input polynomials and product polynomials. First idea on the board. The distributive law says at times the quantity b plus c equals a b plus a c applied to polynomials. The law extends to every term of polynomial 1 multiplies every term of polynomial 2, and the resulting products all add together. For example, the product of the polynomial 3x plus 5 and the polynomial 2x minus 4 expands as 3x minus 3x times 4 plus 5 times 2x minus 5 times 4, which equals 6x squared minus 12x plus 10x minus 20, which collapses to 6x squared minus 2x minus 20 after combining like terms. Second idea. Polynomial multiplication preserves structural relationships. The degree of the product equals the sum of the degrees of the input polynomials. A degree 2 polynomial times a degree 3 polynomial produces a degree 5 polynomial. The leading coefficient of the product equals the product of the leading coefficients of the inputs. A polynomial with leading coefficient 4 times a polynomial with leading coefficient -3 produces a polynomial with leading coefficient -12. The constant term of the product equals the product of the constant terms of the inputs. These relationships are useful for spot checking work and for predicting the shape of the answer before doing the algebra. The number of distribute and multiply steps in a polynomial multiplication problem equals the number of terms in the first polynomial times the number of terms in the second polynomial. A binomial times a binomial requires 4 pairwise products. A trinomial times a binomial requires 6 pairwise products. A trinomial times a trinomial requires 9 pairwise products. After all the pairwise products are written down, the like terms rule from the previous lesson collapses them into a clean polynomial in standard form. Today we drill this on a binomial times a binomial example and a trinomial times a binomial example and lock in the distribute, then collect mechanic for the rest of section 7. Polynomial multiplication uses the distributive law applied repeatedly. Every term of polynomial 1 multiplies every term of polynomial 2, and the resulting products are summed and collected by like terms. The fundamental identity is the quantity a plus b times the quantity c plus d equals a c plus a d plus b c plus b. Each of the two terms on the left multiplies each of the two terms on the right, producing 4 pairwise products. The 4 products are added together, and any like terms among them collapse via the like terms rule. When multiplying two polynomials each of more than one term, the work is the same. Every term of polynomial 1 multiplies every term of polynomial 2. If polynomial 1 has m terms and polynomial 2 has n terms, there are m times n pairwise products. After writing them all down, group like terms together and combine their coefficients to produce the final polynomial in standard form. Polynomial multiplication preserves structural relationships. The degree of the product equals the sum of the degrees of the input's degree m plus degree n. The leading coefficient of the product equals the product of the leading coefficients. The constant term of the product equals the product of the constant terms. These relationships let you spot check the leading and trailing pieces of any polynomial multiplication answer before doing the full algebra. The mechanic is mechanical and exact with no judgment calls. Distribute every term of poly 1 through every term of poly 2, collect like terms, write in standard form. Today, we drill the mechanic on two examples and lock it in for the rest of the section, where polynomial division and equation solving will both build on top of multiplication. The 4i rule from many algebra textbooks is just the binomial times binomial special case of this mechanic, with the four pairwise products labeled first, outer, inner, last. Here is the first worked example. Multiply the polynomials 3x plus 5 and 2x minus 4. Both are binomials, two terms each. Expected number of pairwise products 2 times 2 equals 4. Set up the four pairwise products using the distributive law. 3x times 2x is the first, 3x times negative 4 is the second, 5 times 2x is the third, 5 times negative 4 is the fourth. Each is a single term times single term multiplication. Step 2. Compute the first product. 3x times 2x equals 6x squared. Multiply coefficients 3 times 2 equals 6. Multiply variable parts x times x equals x squared. Step 3. Compute the second product. 3x times negative 4 equals negative 12x. Multiply coefficients 3 times negative 4 equals negative 12. The variable part is x to the 1, unchanged. Step 4. Compute the third product. 5 times 2x equals 10x. Multiply coefficients 5 times 2 equals 10. The variable part is x to the 1. Step 5. Compute the fourth product. 5 times negative 4 equals negative 20. Multiply coefficients 5 times negative 4 equals negative 20. Both inputs are constants, so the result is a constant. Step 6. Sum the four products and collect like terms. The expanded sum is 6x squared minus 12x plus 10x minus 20. The two middle terms minus 12x and plus 10x are like terms, both with x to the 1, combine their coefficients to negative 12 plus 10 equals negative 2. The result becomes 6x squared minus 2x minus 20. Step 7. Verify the structural pieces. Degree of product is 2 equal to 1 plus 1 degrees of the inputs. Leading coefficient of product is 6 equal to 3 times 2. Constant term of product is negative 20 equal to 5 times negative 4. All three structural checks pass. So the product is 6x squared minus 2x minus 20. The big lesson from this example is the distribute collect mechanic on the simplest case, two binomials. The four pairwise products and the single like term collapse are typical of foil-style binomial multiplication. The same mechanic scales to longer polynomials with more pairwise products. Here is a second worked example. Multiply the polynomials x squared plus minus 2 and 4x minus 5. The first is a trinomial with 3 terms. The second is a binomial with 2 terms. Expected number of pairwise products 3 times 2 equals 6. Step 1. Set up the 6 pairwise products. Each term of the trinomial multiplies each term of the binomial. The 6 pairs are x squared times 4x, x squared times negative 5, 3x times 4x, 3x times negative 5, negative 2 times 4x, negative 2 times negative 5. Step 2. Compute each product term by term. X squared times 4x equals 4x cubed. X squared times negative 5 equals negative 5x squared. 3x times 4x equals 12x squared. 3x times negative 5 equals negative 15x. Negative 2 times 4x equals negative 8x. Negative 2 times negative 5 equals positive 10. Step 3. Sum the 6 products. The expanded sum is 4x cubed minus 5x squared plus 12x squared minus 15x minus 8x plus 10. Step 4. Collect like terms. The x squared terms are negative 5x squared and 12x squared. Combined they give 7x squared. The x terms are negative 15x and negative 8x. Combined they give negative 23x. The cubed and constant terms have no partners and stay as they are. Step 5. Write the result in standard form. The result is 4x cubed plus 7x squared minus 23x plus 10. Descending order from x cubed down to constant, standard form complete. Step 6. Verify the structural pieces. Degree of the product is 3 equal to 2 plus 1 degrees of the inputs. Leading coefficient of product is 4 equal to 1 times 4 leading coefficients of the inputs. Constant term of product is 10 equal to negative 2 times negative 5 constants of the inputs. All three structural checks pass. So the product is 4x cubed plus 7x squared minus 23x plus 10. The big lesson from this example is that the distribute, then collect mechanic scales mechanically. More terms means more pairwise products, but the structural rules and the like terms collapse remain identical. Polynomial multiplication is therefore one of the most reliable algebraic operations once the mechanic is internalized. 3 mistakes that catch every algebra student during their first weeks of polynomial multiplication work. Each one is fixable with a small explicit habit applied on every problem from now on consistently. First mistake, missing a pairwise product when distributing. A student multiplies the binomial x plus a times the binomial b plus c and writes the answer as xb plus a c, omitting the cross terms xc and a b. The mistake is a count error. A binomial times a binomial requires 4 pairwise products, not 2. The fix is to always count the expected number of pairwise products at the start, m terms times m terms, and to verify that exact count of products is written down before any combining begins. Counting pairwise products is the simplest spot check and prevents the entire missed term mistake category. Second mistake, dropping a sign during one of the pairwise products. A student multiplies negative 5 times 3x and writes positive 15x, forgetting that negative times positive is negative. Sign errors compound and corrupt the final answer. The fix is to always track signs explicitly during every pairwise product, treating the sign as part of the coefficient. Negative 5 times 3x equals negative 15x, no exceptions. After all pairwise products are written, double-check each sign before moving to the like terms collection step. Third mistake, skipping the like terms collection step and leaving the answer in expanded form. A student writes negative 5x squared plus 12x squared minus 15x minus 8x plus 4 cubed and treats this as the final answer, when the correct final answer is 4x cubed plus 7x squared minus 23x. The like terms collection is mandatory. Expanded answers are not standard form and are marked wrong on tests. The fix is to always do the collection step explicitly, group by exponent first, then write the final standard form result. Polynomial multiplication shows up across factoring, combinatorics, signal processing, and cryptography continuously. 4 broad sectors below where every working professional applies these multiplication operations routinely. In polynomial root finding and factoring, multiplication is the inverse operation. To verify that a polynomial factors as a product of smaller polynomials, multiply the factors back together and check that the result matches the original. Every factoring exercise in section 8 of this course requires polynomial multiplication for verification, and every quadratic equation solved by factoring requires multiplication to check the answer at the end. In combinatorics and discrete mathematics, generating functions encode counting problems as polynomial expressions. To count ways of combining items from multiple sets, multiply the corresponding generating polynomials together and read off the coefficient of the target term. Generating functions are a powerful technique used in computer science algorithms, statistics, and pure mathematics, all built on top of polynomial multiplication. In signal processing and electrical engineering, the convolution operation, which combines 2 signals into a third, is mathematically equivalent to polynomial multiplication when the signals are represented as coefficient sequences. Filtering, image processing, audio effects, and digital communications all use convolution continuously. The fast Fourier transform algorithm, which underlies most modern signal processing, is essentially a fast way to compute polynomial multiplication. In cryptography, public key systems like RSA and elliptic curve cryptography use modular polynomial arithmetic over finite fields. Key generation, encryption, and decryption all reduced to operations on polynomials of large degree. The security of these cryptographic systems depends on the computational difficulty of certain polynomial problems, and the polynomial multiplication mechanics from this lesson are the foundational building blocks of all modern public key cryptography. 3 things to take with you from this lesson today. Polynomial multiplication is the next polynomial operation after addition and subtraction, and it uses the distributive law applied repeatedly across every term of both polynomials. Today's mechanic is the foundation of factoring, polynomial division, polynomial equation solving, and a great deal of the symbolic manipulation work in the rest of Section 7 and beyond into the rest of algebra and into precalculus and calculus. Practice this mechanic until it flows without conscious effort, because it shows up continuously and is the workhorse algebraic operation for everything that follows. First, to multiply 2 polynomials, distribute every term of the first polynomial through every term of the second polynomial without exception. If the first polynomial has m terms and the second has n terms, write down all m times m pairwise products before doing any combining work whatsoever. Each pairwise product is a single term times single term multiplication. Multiply the coefficients, add the exponents on the variable, and carry the sign through. Track signs carefully through every single product because sign errors here are very common and very costly. Second, after all the pairwise products are written down on the page, collect like terms by grouping terms with matching exponents and adding their coefficients carefully. The collection step is absolutely mandatory at this stage of the work, and the result must always be written in standard form, descending order by exponent, leading term first ending with a constant term at the very end. Skipping the collection step or leaving the answer in expanded form is one of the most common mistakes in this section, and it costs points unnecessarily on tests and homework. Third, polynomial multiplication preserves 3 useful structural relationships at the boundaries of the result. The degree of the product equals the sum of the degrees of the 2 input polynomials added together. The leading coefficient of the product equals the product of the 2 leading coefficients of the inputs. The constant term of the product equals the product of the 2 constant terms of the inputs. These 3 structural checks let you spot check polynomial multiplication answers very quickly before submitting your work. Coming up next, the lesson called Special Products, which introduces the FOIL acronym and the patterns for squaring binomials, the difference of squares, and cubing binomials in detail. These special multiplication patterns are pure shortcuts based on today's general mechanic, and recognizing them on sight saves enormous time on factoring problems coming up in the next chapter.